Here we go. That's what we're solving, right? So let's see if I got this one right. Because I had to patch it all up after I rotated it. Here we go. Do you like this? I rotated it for the next homework assignment. So it'll come out when we do the next one, like what everyone else in the world gets. So, I mean, this is, all the physics is right here. This is it. The rest is, once you have this, correct. It's just plug and chug at that point. You're back to your, I guess I checked it just to make sure that these two are complex conjugates of each other, and they are, as they must be. And once you get that, you have your 2x2 matrix, and we should be pretty good with 2x2 matrices by now. Yep. So the only thing is this is now a function of kx and ky. But I mean, this is the same dispersion relationship you had before, where you had t of k here instead of v of k. And so this is the same form, and then you just have to figure out what this magnitude of v squared is. So, I mean, everything looks the same as what you've done before. It all boils down to this 2x2 matrix. And once you know what v of k is, then you can just plot that energy dispersion as a function of k. And then once you have your dispersion, then, I mean, the rest is just, since I tell you where to look for the minimum, I mean, it's kind of, if someone doesn't tell you in advance that the minimum, that, you know, the band edges or the bands meet at these k points, it's not easy to find. At least it wasn't for me. I mean, if you try to take the, you know, derivative of this expression with respect to k instead of equal to 0, you end up with a friggin' mess.
Really?
I did.
On the computer? It doesn't just spit out?
Okay. I don't do derivatives on the computer. I mean, I took the derivative, you know, with respect to kx.
Oh, okay. That would be a mess, yeah.
Yeah, it was a mess.
Yeah, that would be a mess.
Tried to solve for where it was 0, right? I mean, that's how you find a minimum in your math course. It's kind of messy.
I also couldn't find nothing.
Yeah, you just, it's, as I say, and it's easier to just plot it and look at it. Where the, so I guess, you know, if delta was like the difference in the A and the B site energy. So if that's 0, then your bands are going to touch because V of k goes to 0 at these special k points, at these 6 k points. And delta equals 0, blah, blah, 6 points, blah. And then, yeah, so then you just have to show that V goes to 0 at these k points. So I guess we just need to check k1 because why? The cosine is symmetric with respect to the sign of the argument. So I guess everything shows up in that cosine, right? V of whether kx is positive or negative doesn't matter, or ky is positive or negative because cosine is an even function. And so, you know, k1 and k1 prime is just negative of k1. k2 is negative k2 prime. So I think those 4 k points were like, you know, plus or minus 1/2 and plus or minus 3/2. So just checking one of them gives you all 4. Yeah, you'll find I'm lazy if I can skip, you know, if I can use a slick argument to skip a lot of steps. I'll do it every time. Okay. And I guess K5 and K6 are probably just plus and minus of each, plus and minus 1 here. So you just need to check one of them. Oh, and I guess I go on to the linearization problem. I guess I have the solution for both of them here, so I can't show you that since that's the next problem. The next homework assignment. Yep. All right. So you all, let me see that. That's a beautiful picture. Is your name on it? Okay, good. Wow. So is it just with MATLAB, or how do you do this? MATLAB. All right. Okay.
Excuse me, the t equal to 4, right?
What's that?
The t equal to 4.
2.7.
7?
2.7.
2.7?
Oh, actually, I think I said in class use 3 or 2.7 doesn't matter. Those are numbers people use in the literature, either 3 or 2.7.
Okay, I use the 2.
That's fine. 2.7 is a fine number.
No, I equal to 4.
What's that?
I mean, that one I equal to 4.
What's equal to 4? Your t was 4.
Yeah, T is 4.
Okay, so I mean, you got the right shape. It's not going to change. It's just going to change sort of the height, but it's not going to change the overall shape or anything like that.
Yeah, the shape doesn't change.
Right.
Yeah.
All the minimums are still at k. We'll see in the next homework assignment that the velocity and the slope is proportional to t. So your electrons are just moving a little faster than ours. That's all.
Maybe I'll change it.
No, don't worry about it. 4 is fine. Just make it clear what you used. You've got really fast graphene.
Yes.
Really fast.
Wait, so T represents the...
The coupling, the hopping between the sites. So if it's bigger matrix element, it means they couple more strongly, which means they can move faster.
So the group velocity is faster? Or no? Is that not the right way to say it?
Well, yeah, that's the right way to say it. Especially since, for graphene, we're going to see it's a linear dispersion.
So if you smush something in that direction, it'll make it faster.
Make it slower,
Makes it slower?
right? The slope gets less. The velocity is proportional to the slope of E versus K.
Okay, wait, no, I'm thinking about that effective mass then. So effective mass gets bigger if you smush it.
If you smush it. So is a heavier object moving faster or slower? Use your intuition.
Yeah, okay, so slower.
Yeah.
That makes sense.
Really heavy doesn't move much.
Okay.
Yep.
So
It's
if
very
we
intuitive.
apply a strain, we can modify the mobility. Yeah?
What's that?
If you apply a strain,
Yeah?
you can.
Yeah, you'll deform it. Then you'll deform your Brillouin zone, right? But it's very tricky as to whether, if you just have graphene,
The distance
You-
become higher.
you don't, it's hard to create a gap with strain. I mean, you'd have to just go through if you just do like linear strain, small, in the usual way, very small, like linear order strain. I went through that once. You don't get a gap. There's no gap at all. But, if you really deform the thing, then I've seen papers where they claim they get a band gap out of it.
So it's possible for bilayer. Yeah?
Oh, you bilayer, yeah. But, bilayer, ideal bilayer, there's no gap. You get 2 parabolas that touch at the K points, no gap. You still have to you have to change the potential of one layer with respect to the other to get a gap in the bilayer.
Do you get the same property in if you make a tube out of
The
it?
carbon nanotube?
Yeah,
Which property is that?
just the same band structure.
Well, once you make a tube,
Period.
then you only have like, it becomes a one-dimensional system. You only can define your K along the axis of the tube. And I almost don't want to get into this. It'll just confuse the heck out of everyone.
Oh, okay.
But
Don't worry about it. I was just curious if you could do that to, I don't know.
What it does, so, okay, I'll just confuse the heck out of everyone. That's the way it goes. If you roll up your sheet, do I have the picture here? So you take your sheet, and you kind of need a bigger sheet to show what happens, and you roll it up. And you can roll it up in a lot of different ways, and that's called the chirality of your carbon nanotube. So one way is to just, take these ends and roll it around so they touch these ends. And that would be a zigzag tube. And the other way is, if I want to have the armchair, how do I have to roll this thing? I can't see it right now. Okay, there's 2 ways that you see most often. They call them armchair and zigzag. Like if you do I can't quite see how to get my armchair edge here. Everywhere I look, I get zigzag.
That A on this A.
What's that?
Or the
It's A on.
That A? We'll give. Oh, okay.
So B A.
I'm trying.
The straight up direction is 1.
Straight up, I'll get zigzag if I just roll it. Okay, so I can't quite. How do I show it? Okay, we won't. Oh, I see. So it leaves an end to the tube that looks like this, and then it repeats. But this is why they call it armchair. It's like you're sitting in this nice little chair with arms on it. This would give you what the end of the tube would look like. That would repeat around the end of the tube, and you have an armchair tube. Okay, now, if we have a continuous K vector in 2 dimensions now. Once you roll it, you still have a continuous K vector along the length of the tube, call it KZ, right, along the axis of the tube. But now you have, and the reason is continuous, remember, it's like 2 pi over L, and we let L go to infinity. So it becomes that's like the change delta K. But once you roll it and have L is now the sort of that circumference of your tube when you roll it in that other dimension, say ky. And that circumference is not infinite. That circumference is whatever it is, like 10 atoms, 20 atoms. And so now your delta K is, again, 2 pi over the circumference. But that's now a discrete variable. And so you have these discrete Ks in the roll-around direction. In the same way, like in a particle in a box, where you have discrete wavelengths that fit in your box. Now you have, because it still has to be periodic around the circumference of the tube, and there's only discrete wavelengths that will match that period, right? Integer multiples of the circumference, right? And so what you do to understand what happens, now we're in K-space, right? This is the K-space version. This would be our fundamental Brillouin zone. So depending how I wrap it, say I wrap it so it, in the vertical direction. So this is still a good continuous K vector. But along this direction, my K, Kx, becomes a discrete K. And I only have discrete Ks allowed. So if I can draw on this, let's see if I can draw on this. Markup. So if you have discrete Ks, your discrete Ks, like you can have probably K equal to 0, and then another K, 2 pi over the circumference away, and another K, 4 pi over the circumference away, like that. So you're going to have discrete Ks in the x direction. And so these are the allowed K values. And if one of these lines goes through a Dirac point, then your carbon nanotube is metallic. If one of these lines, these discrete lines, because goes through a K point, then I got the lines going the wrong way. My bad. They should be going vertically, right? Because Ky is continuous, Kx is discrete. So if one of these discrete lines goes through a K point, then it's metallic. So I might have 1 and 0, and I guess I'd need one to go through like these K points here, and there'd be others. But if it goes through a K point, that means you go right through that point where they touch, and your carbon nanotube is metallic. If you roll it another way, you still have a discrete set of lines. They don't go through the K point, and now you got a semiconducting tube. And this is what they call determined by the chirality of the tube, how you wrap it, and and exactly what that circumference is. So you can imagine that was really hard to control, and that's one reason why carbon nanotubes kind of, among other things, didn't really become like the semiconductor of the future, like everyone predicted for a while, because they couldn't control whether it was metallic or semiconducting. Towards the end, they could control it maybe with 95%. I mean, the chemists got really good. But if you think in your integrated circuit, you want 1 billion transistors that work well, and 5% error means that's a lot of transistors that aren't working. Right? 5% of 1 billion. That's unacceptable error. So that's what happens when you roll it up into a carbon nanotube. Some are metallic, some are conducting. It just depends whether these discrete lines in K space go through a K point or not.
But it would still have the good properties of having like what graphene would have, but now it has.
So the metallic ones would still have this linear dispersion, be very fast, and all this good stuff. Yeah. And the semiconducting ones they even like better because they were semiconductors, and you could make a transistor out of them and a band gap. You could gate them, you could turn them on and off. People love them. It's just that from a manufacturing point of view, it was like they weren't controllable enough.
So, by them being fast, does that mean they're very low resistance? Is that
the velocity is really good. Mobility was really good. It turns out, on top of everything else, the first optical phonon was about 200 millivolts, which is like 10 kT at room temperature. And the optical phonons are the things that really kill your mobility. They cause a huge amount of scattering. So you have to, apply about 300 millivolts of voltage before your electrons can really start seriously scattering. And on top of that, they have a really high velocity. So, they were really great, these things. Or a lot of, from an electronic point of view, everyone was really in love with them. And they're self-passivated. The surface has no dangling bonds. They aren't gonna bond with stuff in the environment that easily.
But that doesn't mean the signal travels faster, does it?
Yep.
The signal
Sure
travels
does.
faster? Because how fast would signal travel in copper? Isn't that close to the speed of light?
Oh no, we're talking about. So usually now you're talking about transmission lines and going to transmission line theory and that LC, right? The group velocity in a transmission line is like 1 over the square root of LC or something like that. I can't remember.
Do you focus on
Any EEs remember the transmission line theory?
So do you focus on the group velocity for that kind of stuff, or the phase
you
velocity?
always focus on the group velocity.
So the phase velocity doesn't do anything. Okay.
And in electronics, it really has more to do with the velocity of the electrons moving. It's real electron charge moving through the device from source to drain. Anything else? Because this is our discussion combined with whatever we have time left over to make up. So we can discuss. I like discussion.
Excuse me, sorry.
Yeah.
If you roll it up, so it's going to be just a PZ orbital, PZ bonding again?
Okay, if you make the circumference really tiny, then you start getting matrix elements between the PX, PY, and the PZ. And you start getting hybridization, and that changes the picture. Once you start getting diameters below a nanometer, and as you get really tiny, then you have to really worry about the other orbitals. And if you think from a band point of view, what happens is the sigma bands and the pi bands start mixing, because you start getting matrix elements between the PX, PY, and PZ orbitals, which you don't have in a flat sheet. So it's just a matter of the curvature, and those PZ orbitals start tilting in a little bit.
Yeah. Dispersion is different.
So that starts changing. Once you start getting that, it's like you just have to do the calculation, see what you get.
So do they have like computer models where you can just like stick a thing here and stick another one there, and then it generates like just a plot of what it is?
What people these days just run when they have something that they need to get some insight into, and it's not necessarily known a priori, is just to run density functional theory code, which takes into account all the orbitals, and it will spit out an EK.
Do they mostly use MATLAB for this kind of stuff, or do they use a different type of programming?
They definitely do not use MATLAB. They use these density functional theory codes have been developed for like 30 years or longer, and they all seem to come out of Europe, and often out of Germany. One of the favorite ones is out of Austria, and it's still written in F90, And it's just
F90?
all the scientific codes originally, started being written in the 60s, and the scientific computing language was F70. Well, in the 60s, it wasn't even F77. I don't know what was before F77. F something. I don't know. So, right, F77 was Fortran 1977. That was a big. So a lot of code was written in F77, and then in the 90s, they upgraded to F90 and had a little more. They had things like pointers, which they didn't have in F77. You've never even heard of it, have you?
I've never even heard of F90.
Have you heard of Fortran?
I've heard of Fortran.
Okay, it's all flavors of Fortran.
Oh, that's what that
It's
is?
Fortran.
Oh,
Yeah,
okay.
Fortran. So most of these scientific codes, since they started being developed, last century, they're in Fortran, and they still are because it's just too much work. And there wasn't a lot of incentive. What would you do? You could convert them into C, C++, but it turns out that maybe they're about the same now. But because everything was initially developed in Fortran, all the packages for large matrix manipulation were written in Fortran. And all the compilers for Fortran were far better optimized for scientific computing than the C compilers. So for a lot of historical reasons, Fortran was just faster for high performance computing like this.
I guess faster is a lot better because these calculations probably take a long time. Then, right?
Faster is always better. Always better. Even if it's just 5 minutes versus 2 minutes, faster is better. But these do take a long time, and they suck up a lot of resources depending on what you're trying to do. I mean, yeah. I don't know. I don't know how many cores we generally, like when Shan submits a job or something. We do most of our production stuff on the TerraGrid out there on Texas or San Diego or something like that.
So just much stronger, much faster computers than
it's
just a standard.
Huge. Everything's gone to sort of, clusters of Linux cores, basically. And we're running Fortran code still.
Interesting.
I mean, what the students write here is mostly MATLAB and C++. No one's writing Fortran. Unless they, have to, modify something in an old code. Well, what's LAMPS written in? Is LAMPS in C?
C++.
C++? So that's been rewritten, I guess.
Maybe.
Yeah.
Because in molecular dynamics, you will always use the lamps.
Right.
Except that maybe, let me see. Nothing else maybe. Lamps is better because it's free and strong.
What is LAMPS?
That's a molecular dynamics code.
Yeah.
Is that a library or is that a?
It's sort of a more classical solver. It needs force fields between atoms, and then it can model things like thermal transport, vibrational motion of the atoms. But it's a more classical type stuff. It's not based on Schrodinger's equation like what we're doing.
Oh, okay.
But the force field is based on.
So they run like a density functional theory code based on Schrodinger's equation to get the force field, which then they feed into this code to do the molecular dynamics. Otherwise, I'm going to have to drag you back into spin orbit coupling, and I know you're not going to be happy.
Is the next homework going to be about spin type stuff? Then?
No, well, the next one is going to be continuing on in graphene, going from
Okay.
where you are now to linearizing what you have and getting this Hamiltonian that you will see if you pick up most physics papers on how the physicists think about graphene to get what you call the linear dispersion.
Are you going to talk about K.P?
Yes, but maybe not today. Hopefully, I'll finish up the spin today, and then the next thing is K.P. You really want K.P? Okay.
Actually, the left use C++ is because it's easy for others to add new code,
Yeah.
new functions.
Right. Yep.
Maybe Fortran is difficult.
Yep.
for
It
most
is.
of the
It is.
developers.
It is.
I just come up with design.
Oh, it's definitely if you have multiple people developing. Okay, so this is where we were before spin-over coupling. And then we started looking at spin-over coupling. And this is a Hamiltonian that we have to deal with. And we have to calculate the matrix elements of this thing. And as I said, it's spatially it's local. So it's only going to give you matrix elements between orbitals on the A atom with other orbitals on the A atom, but nothing that connects the A atom to the B atom. And it will also give matrix elements between orbitals on the B atom and other orbitals on the B atom. And so we've been trying to figure out, this is what we've been doing, going through the steps needed to calculate the matrix elements of this thing. So, well, here was our little cartoon of the physics underlying spin-orbit coupling.
Why the term become important in heavier atoms? And when it's important? We usually do not use it. But
There is more angular momentum as you go to the heavier atoms, right? L is L dot S, and L is like P, D, F. So,
what is L?
well, I mean F orbitals, right? I don't know if that's the full explanation, because even if you just go down the periodic table, like in group 3, indium arsenide will have more spin-over coupling than gallium arsenide. And the valence band for both is pretty much p-type. But again, if you think of L dot S, once you have d orbitals, right? L is 2 for the d orbitals. L is 3 for the f orbitals. That might be one simple.
So in metals it's important.
For the heavy metal, for the transition metals, you get large spin orbit, like in platinum. Transition metals, where the d orbital, the valence shell is in the d band, the d orbitals. You have often large spin orbit coupling. Okay, and then we said, well, if we look at this total angular momentum squared, and go ahead and square it, we end up with this thing on the right-hand side, which looks like the Hamiltonian that we want to calculate the matrix elements of. So we simply rewrite L dot S like this: it's J squared minus L squared minus S squared. And that's the thing we're now going to calculate the matrix elements of. And to do so, we transform our basis from this mixed representation, a direct product representation between the orbital angular momentum and the spin angular momentum, into a total angular momentum basis. And that's what we spent a good chunk of last time doing. And the way you do that is make use of these tables of what's called the Clebsch-Gordon coefficients. This, this expression in the red box is our usual approach to doing a change of basis. And these matrix elements that I, with the underlined with the curly bracket, those matrix elements are tabulated in many books and described for those who are curious. I like these descriptions best. And this is the table of matrix elements. Between the on the left column is that direct product basis, and on top of the matrix is the direct product basis. You just read across to find the matrix element you want, and that's how you evaluate that sum that we wrote down. And then we just went ahead and did that, converting our old basis into this as a linear combination of these direct product, of these total angular momentum states. So our old basis, which was itself a linear combination of these y's, are px, py, and pz, and each of the y's you write as a linear combination of the total angular momentum. And then you write the p's as a linear combination of the y's, and so you end up with these big expressions for the basis states that we work in terms of these total angular momentum states. So we went ahead and did that, and we got them all, and this is what they are. And so now the next thing we have to do, and what we'll do now, is finally we're in the position to evaluate this matrix elements of our spin orbit coupled Hamiltonian. At any rate, so let's go ahead and do this. So we're going to evaluate the matrix elements, and I'll do it for one because it's kind of messy, and then just write down the answers for the rest of them. Let's look at, so px orbital on the A, and so it's all, as I said, because it's a local interaction, all the orbitals for the one I'm doing will be on the A atom, and the B atom will work out exactly the same way. And, well, the way we do that, we first just write out HSO in terms of that J squared minus L squared minus S squared. And we expand out these bra and ket in terms of their linear combination of direct product states. So that's lambda A over 2. I don't know. Did you all realize I was going to do a makeup to like 5? Did you? I saw you looking at your watch. Did you realize I'm going to do a makeup lecture here for the one I missed?
Yeah, that's fine.
Did I forget to mention that in that announcement? Sorry.
Fine. That's fine.
I wonder if you did the screen recording.
Yeah, it should. Yeah, it's being recorded.
Okay.
Yes.
We are leaving for
always have the Zoom meeting at 4.
Okay. All right. Okay. All right. I guess I could sit here by myself and do. Sorry, I forgot to. I forgot to mention that in the announcement. So if you got to go, you can go. And so XA up, if you go back and look at your notes, this was equal to 1 over root 3. 3 halves, negative a half. So that's our XA up. So, and these are all on the A atoms. I'm not going to write A for every bra there. And then we're the HSO is at, so that's my HSO. And now I've got my ket on the right side, which is this YA up, which then I write out in terms of its whole deal. And now recall that each one of these bras, each one of these states, which are the total angular momentum states, are simultaneous eigenvectors of J squared, L squared, and S squared. So in this basis, all these operators are diagonal. All these operators are diagonal in this total angular momentum basis, which means that this bra is only going to have a matrix element with this ket. Similarly, this bra will only have a matrix element with this ket. And finally, bra will only have a matrix element with this ket. Because in this basis, all these operators are diagonal, and this is an orthonormal basis. Right? So when this J squared minus L squared minus S squared hits any one of these kets, it just gives me back that ket times some number. And then I close the inner product with this bra from up above, and because of orthonormality, it's only going to give me a non-zero when they hit each other. And so then all we need to know is, well, what are the we've written them down. Let me write them down one more time. What are the eigen values corresponding to these different operators? Okay, for now, let's just get through calculating this matrix element here. So we know what this, we now know what this operator, which is this guy here, we now know what this operator does when it hits each one of these kets to the right, which is actually below it now, right? Each one of these kets to the right. And if you look at this, the only thing that's going to vary is the value coming from this guy, because this can give me either that's 15 quarters or 3/4, depending on the total angular momentum, whether it's a 3 halves or 1/2 state. the L squared and the S squared always give me 2 or 3/4, because L for every one of these states is 1, S is 1/2. So what I get from the L squared and the S squared term never varies. It's only the J squared term, which depends on the value of J, whether it's a 3/2 or a 1/2 state. Okay, so let's see if we can write this down now finally. Guess we can do them one by one. So we'll start with the 3/2 negative 1/2 state. And each one of them has a 1 over root 3 in front of it. So those multiply together to give me a 1/3. And I guess I have to go back and understand this. I had initially, this I is going to, this factor of I is just going to go along for the ride. My lambda A over 2 is going to go along for the ride. Every matrix element has an h bar squared, which I'll factor out. And it looks, I think, I threw it away, but I think I should have a 1/2 out in front of this guy. And I have to go back and understand why. So let me just take out my constants. I'm going to have out front a I, lambda A, h bar squared, since every matrix element will have an h bar squared in it, and all over 4. That gets rid of all my constants. And now I'll go through the matrix elements one by one. So first we'll look at those two states underlined in red. And so when J squared hits that, well, that's a 3/2 state. Well, first the two factors of 1 over root 3 get multiplied together to give me a 1/3. Right? They just go along for the ride. The two factors of 1 over root 3. They give me a 1/3. Then J squared hitting the 3/2 state gives me a 15/4. And then, well, minus L squared always gives me -2. And minus S squared always gives me -3/4. So that's what I get from the two states underlined in red. That's the term I get from the two states underlined in red. And now I'll do the two states underlined in green. So that's going to give me plus, and the two factors of root 2 over 3 multiply together. The minus signs multiply together to give me a plus sign, and so I just have a 2/3 out front. And this is a 1/2 state, so when J squared hits a 1/2 state, I just get, what do I get? What do I get from the 1/2 state? 3/4? 3/4? Yeah, 3/4. And then again, the L squared and the S squared always give me a -2 and a -3/4, so -2, -3/4. And then finally, the two states underlined in yellow, and I'll use light green, so maybe it'll show up better for that. So the two states underlined, they have alternating signs, so I'll get a minus sign out front. Right? One's plus, one's minus. And it's a 3/2 state. Oh, and there's no coefficient out front. A 3/2 state, which means I'll get 15/4 -2 -3/4. And that's it. That is the matrix element. And I just add them all up. Well, it turns out if you do, this is actually 1. This is actually -2. And this guy is 1. And so I end up with, it's really annoying, like in physics you go through so much work and like you end up with like 1. So I, lambda A, h bar squared over 4 times 1/3 minus 4/3 minus 1, which is finally, after all this work, is equal to minus I lambda A h bar squared over 2. That's it. That's our matrix element.
You said that there's no elements between the red and like green or
Right.
Would you please repeat why one more time?
So when this, here's our operator here, this j squared minus L squared minus S squared, right? When that hits any one of these states down below it, that state is an eigenvalue of that operator. So I just get that same state back, multiplied by a number. And then so now I've got a number times that state, and now I come in with the other state. But these are all orthonormal states. And so I'm just collapsing, the number goes out, it's constant. And orthonormality just kills off any cross sort of matrix elements.
It's an imaginary number.
It's imaginary.
It's diagonal on the diagonal terms.
It's not going to be on the diagonal because, right, it was a matrix element between. I mean, it's in the diagonal block, but it's not a diagonal matrix element because it was between an x and a y orbital, all on the A atom. But so before that, well, that whole block was completely diagonal. Now this gives some off-diagonal matrix elements. Okay, these matrix elements are written in terms of the spin-orbit splitting parameter. So we don't actually write them like this. We write them, define a different parameter. So we define a parameter delta, which is equal to, and you'll see why we do this in a moment, 3 lambda h bar squared over 2. And often you'll see this in parameter tables listed as delta SO. So this is a parameter you can find in, like, when people write down band structure parameters for different materials like gallium arsenide. This is a spin orbit coupling parameter. And so using this, our matrix element, finally at the end of the day, the final matrix element, XA up, HSO, YA up, is equal to minus I delta A over 3. And since if you have 2 different type of atoms, you'd have 2 different, so it's supposed to be a delta sub A over 3. This would be your final form of your matrix element. Okay, so without dragging you through the gory details, there are 6 non-zero matrix elements. And I'm just going to write them down. All right, those are all of the 6 non-zero matrix elements you get. And these are all for orbitals on the same atom. The HSO does not couple the A atom to the B atom. And so you add these 6 matrix elements to either to the AA and whatever you want to call them, BB or CC blocks of your Hamiltonian. So the AA and CC block of your Hamiltonian matrix. Right, I mean, in sort of schematically, we wrote it as like the A block and the C block, the A block and the C block. Right, so these matrix elements would go in here and go in here. Right, they affect those blocks. They don't affect the coupling between the A atom and the C atom. Is where these guys go in. And so if the A atom is different, if you have an anion and cation, then in the tables where you can find these tight binding parameters, you'll find a value for, you'll find two different values, a value for the gallium and a value for the arsenic atom. And they'll be different. And since both the AA block and the CC block are going to have exactly the same form. So I'm going to write down what one of those blocks look like, say the AA block, sp3 up and sp3 down. So these are all going to be down, and these will all be up. And similarly going across the top. Okay, so this formerly was our diagonal. So these, let's see, I should draw the upspin and downspin on. So this is the line that divides the upspin from the downspin. So these will all be upspin, and these guys are all down. Okay, now this would, and they're all on the A atom. So this is all on the A atom. We're not even looking at the B atom. Well, S, you know, the S orbital is completely unaffected by all of this. The S orbital is still just living in its own little world. The p orbitals are where you and the p orbitals do not couple to an s orbital, right? So we can just separate out the s orbital's world from everything else and be done with the s orbital. So there's no interaction between s and anything else. And s up doesn't have any matrix element with s down because, right, its angular momentum is 0. Okay, so we're done with S, all of this, and all of this actually, so all of this is 0, all zeros. Okay, now the P's are where you get all this, all these matrix elements, so we know the diagonals are still going to be the diagonals, so I get, you know, on the diagonal E sub P, that's what we had from before. But now I have the off-diagonal matrix element minus I delta over 3, 0, and it has to be Hermitian, so this has got to be I delta over 3. So you get a coupling between the x and the y orbital that we've already seen, both upspin. You get couplings between upspin and downspin. So way over here, we have a coupling between the x and z. X up and Z down. Coupling between Y up and Z down. Okay, this is I delta over 3 and minus I delta over 3. And then 0, 0. Okay, that is how your diagonal matrix. So before we had spin-over coupling, this was purely diagonal. We just had ES, EP, EP, EP down the diagonal. And then would have exactly the same thing for downspin, since it'd be spin degenerate. And now, once we turned on spin-over coupling, we pick up all these extra matrix elements. And so before, since it's diagonal, you know, we had the holes were threefold degenerate at gamma, and the valence band was entirely made of holes. The conduction band entirely made of electrons. That's still going to be true at gamma. But we're going to break the degeneracy of that threefold degeneracy of the whole band, and we got to show how we're going to break that. The form for the B atom looks just identical, or I keep B atom, C atom, whatever you want to call that other atom. The B atom block as an identical form. It's just that the actual value of, you know, your delta may be different if the atoms are different for the A and the B block. And because it's only coupling locally, all of this stuff is not a function of K. It's on the diagonal block. Okay, so I mean this looks pretty complicated. But at K equals 0, you don't actually look at this. You go back to your total angular momentum basis. And you look at the form of the Hamiltonian in your total angular momentum basis at K equals 0. So we need to look at K equals 0 to understand what happened to our valence band edge. So we're going to look at the gamma point. And if you recall, when we set K equal to 0, we only had one, in terms of the p orbitals, there was only one type of matrix element that coupled the A atom to the B atom. A px on the A coupled, I guess I should be specific, at K equals 0, to a px on, I guess I'm calling it the C atom, on the C atom. Well, let me write them all. The three non-zero matrix elements that we had. Py only coupled to Py, and they're all identical. And Pz only coupled to PZ at k equals 0. And the matrix element for all of them was identical. We call that VXX. Those were the only non-zero matrix elements from coupling the A atom to the B atom at k equals 0 for the p orbitals. And the s orbitals we don't care about because we know they're going to go into the conduction band and they do not mix with the p orbitals at k equals 0. And so what we're going to do is at k equals 0, we write our Hamiltonian matrix in this basis of the pure angular momentum states, our JM states. We're going to write our Hamiltonian matrix in that basis. And we know nothing happens to the conduction band because S is unaffected by spin-orbit coupling. It just stays whatever it was. So we're only going to look at the p orbital subspace. We only need to look at the p orbital, only the matrix elements that involve p orbitals. Okay, for all 6 of these states, of these total angular momentum states, the diagonal element of our tight binding Hamiltonian, not the spin orbit Hamiltonian, so JM H tight binding JM, right? This would be a diagonal matrix element. And remember, this is just a linear combination of the XYZ orbitals. And every one of those orbitals has the same diagonal matrix element, epsilon sub p. And since it's normalized and the sum adds up to 1, this is just, well, epsilon sub p. Just like if it were px, py, and pc. And so you can go back and look, you know, we'll take a simple state, like the 3/2 state. Oh, that's kind of too simple, but that was our -1 over root 2 x plus I y. And so if you take the matrix element of that with, itself with our H-type binding Hamiltonian in between, well, x only hits x, y only hits y. The 1 over root 2 times itself gives you a 1/2, and each, the x hx is EP, y hy is EP, and 1/2 plus 1/2 is 1. So you just get back your EP, because they're all normalized linear combinations of the p states. Right? So all of these, so the diagonal elements you get from the tight binding part are exactly what you have before. And then, so now we only have to worry about the spin orbit part. But these are eigenstates of the spin orbit part. That's why we're doing it like this. And so, for example, 3/2 m HSO 3/2 m. Well, that's just, we've already calculated that. That was our delta over 3. If we go through, going back, if you can write this back out in j squared minus l squared minus s squared if you like. But you get delta over 3. What else do we need? And remember, the only thing matters is whether in HSO, the only thing that changed was the j squared term. And that only depended whether it was a 3/2 or a 1/2 state. So all the 3/2 states have the same, that's why I wrote it as a function of m, right? This is independent of m. So all the 3/2 states, no matter what m is, have the same matrix element. And then the 1/2 states, 1/2 m, have a matrix element of minus 2/3 delta. Do you want me to write that out? How I got my delta over 3 and minus 2/3 delta? I wrote it out in terms of j times j plus 1, l plus 1, s plus 1. Then you add them all together and you get delta over 3 or minus 2/3 delta. So for, let's see, 3/2 m h s o 3/2 m is lambda h bar squared over 2 times 3 halves plus 1 minus 1 times 1 plus 1 minus a half times a half plus 1. Right, that's my L squared, J squared minus L squared minus S squared. And, well, it turns out that all this stuff that's just exactly equal to 1. If you add all that up, you get 1. So that's equal to lambda h bar squared over 2. And from our definition of delta, that's our delta over 3 from the way we defined our delta. And you go through the same exercise with the 1/2 state, and you get that. So if we do the 1/2 state, 1/2 m HSO 1/2 m is equal to lambda h bar squared over 2. And again, the only difference is from the j. So it's 1/2 times 1/2 plus 1 minus 1 times 1 plus 1 minus a half times a half plus 1. And this thing is, I don't know, if you add it all up, you get negative lambda h bar squared, which from our definition of delta is negative 2/3 delta. And so we had 4 3/2 states and 2 1/2 states. And so the 4 3/2 states all have the same energy. Write that down. I guess, so we now have the diagonal. The diagonal elements are either, so the diagonal elements for any, 3/2 state, 3/2 m h tight. So the total Hamiltonian is H tight binding plus HSO. That's just epsilon p plus delta over 3, I guess, right? And for the 1/2 state, independent of whatever m is, that's epsilon p minus 2/3 delta. And now you can see why delta was defined the way it is, because the splitting is delta. The splitting of those states is delta. Right? The difference in those two energies is delta. And that's why it was defined the way it was. So now your valence band at gamma becomes, you've got 4 states that are degenerate at EP plus delta over 3, and these are from the 3/2 states, right? And the 2 states down here, EP minus 2 delta over 3, and these are from your J equals 1/2 state. J equals 3/2 and J equals 1/2. So that's how this is what broke your initial 6-fold degeneracy into 4 and 2. So this will become, so these 4 states here will become your light hole and heavy hole band. Your 2 bands with 2 spins each, right? Because your 3/2 state can have m equal 3/2, 1/2, negative a half, and negative 3/2. So there's 4, and it's not what they call it. You can't think of it as a spin up or spin down anymore. It's a mix. Like up and down is no longer a good quantum number once you turn on the spin over coupling. People just refer to them as these J equal 3/2 states, J equal 1/2 state. And the 1/2 state, so the J equals 1/2 state, they're what form your split off band down here. Split off band. But we're not quite done. So, we haven't, so this is just the diagonal elements. You still have that off diagonal element that couples the A atom to the B atom. So this is just what I get if I completely ignore that coupling. And, well, what about that coupling? The coupling of the A atom to the B atom. How do I take that into account? Well, if we go back and look at this, at k equals 0, we're saved by the fact that x only couples to x, y only couples to y, and z only couples to z at k equals 0. And these Jm states are linear combinations of x, y, and z, and they're normalized. And so if I put in some linear combination of x, y, and z states on this side, and the same combination of x, y, and z over here, I'm just going to get Vxx again, because it's a normalized state. X will only have a matrix element with x, y will only have a matrix element with y, and z, and the matrix element is the same, Vxx for all of them. And you add them all up, just like we did for the diagonal element, you get Vxx again. And so finally, in this basis, our Hamiltonian at k equals 0, it's the perfect time to wrap this up and be done with this. Looks like this. I guess the other thing, I need to point out, not only do you get Vxx, but this off-diagonal coupling is actually diagonal in the total angular momentum state. So a 3/2, like a 3/2 state is only going to couple to a 3/2 state. 3/2 1/2 will only couple to a 3/2 1/2 on like the A to the B atom. Is that easy to show? The higher level concept is that this coupling between atoms conserves total angular momentum. That's sort of like the overreaching concept. And that's why you only get these off-diagonal matrix elements between like a 3/2 state and the same 3/2 state on the B atom. I'll just do an example to prove it's true for one. I mean, sort of, other than saying it's easier to just try, and again, I'll use like the simplest one. So if we look at, say, 3/2 on the A atom, and our tight binding Hamiltonian, and the same, let's do 3/2 and negative 3/2. So 3/2, negative 3/2 on the B atom. Look at that matrix element. And then you have to expand out these things. So this is like
Is that 3/2? 3/2 or 3?
Oh yeah, that's a 3/2. Sorry, 3/2. There we go. 3/2, negative 3/2 between the A and the B atom. And so I write out what these things are in terms of the px, py, pz. I get a negative 1/2 for the 3/2. This was too trivial. I'm sorry. I forgot that's a bad example. Because these guys are all upspin. And the 3/2 negative 3/2 state is all downspin. So of course I'm not going to get a matrix element there. I got to choose something at least where I have the same spins, right? The tight binding Hamiltonian does not couple different spins. And so this guy is composed entirely of downspin states. So of course I'm not going to get a matrix element out of that one. Now maybe I'll make that a homework assignment. It's trivial to just go through them and show that, I get 0 unless they're the same. Just go. So at any rate, what I'm saying is that, so J, the only non-zero ones I get, so this would be on the A atom, H tight binding, J prime, M prime equals, on the B atom, equals our Vxx delta J prime, J delta MM prime. Okay, so it's diagonal. You'll only get something non-zero if M equals M prime and J equals J prime. Given that, finally we can write down the full Hamiltonian matrix in this basis at k equals 0. And you write the things that are going to couple you right next to each other. So I'm not going to try to write all of this. Let me just, how many of these do I have like that? So I'm going to have 4 4 blocks that look just like this, right? There's going to be 4 blocks that look just like this. And so, and they're going to be block diagonal. So 4 blocks, absolutely identical due to those 4 states, the 4 3/2 states. Right? The 4 3/2 states are going to give me 4 2x2 blocks that are identical. And then the only difference is the 1/2 states. So for the 1/2 states, I don't know, I'll just throw them down here somewhere. 1/2, 1/2, 1/2, 1/2. So this is A and B. So somewhere out here, I'd have a block from these guys that would be EP minus 2 delta over 3 VXX, VXX, and same diagonal, EP minus 2 delta over 3. And I'd have one more, I'd have 2 blocks coming out of these 1/2 states. So the other one is like, 1/2 minus a half, and 1/2 minus a half. And I got 4 3/2 states, 2 1/2 states. These are the 2 different type of blocks you're going to get. And since there's no coupling between the blocks, you got a bunch of 2x2 matrices, right? And so this 2x2 matrix gives you its eigenenergies of E, how many times have we done this now? E equals. Okay, so the only difference is before we had spin-orbit coupling, right? Before we just had EP plus or minus VXX. Right? That's what we had without spin-orbit coupling. And now we have this, it's shifted up, the valence band is shifted up by delta over 3. And similarly down here, the valence band down here from this guy is just going to be EP minus 2 delta over 3 plus or minus VXX. And before, we didn't have that 2 delta over 3 term. So before, everything was just EP plus or minus VXX. And so your valence band gets split into this, 4 3/2 states and 2 1/2 states, and making your different bands. It's 5 o'clock. I'll just draw some pretty pictures next time of what the valence band looks like, and then we move on to K.P. And I'll get the new second part of the graphene homework uploaded.